Hello students, and welcome to lesson 7.03, and in this lesson we're going to be covering the concept of pH. We do have some common core standards that will be addressed as we go through this lesson, so if you'd like to pause the video and read over these, feel free to do so. You can also access these in the course under course information and then click on standards. For this lesson, our two main objectives are to determine the relationship between pH, hydronium, and hydroxide ions in a given solution. And for the lab portion of it, we're then going to get into the second part here where we describe the process of titration and apply it to a laboratory investigation. Now, to be able to complete this lesson, we do need some prior knowledge, and those are lessons 2.4, 3.9, 4.6, and then for module 2, or excuse me, semester 2, 5.6, 5.7. And basically all of these lessons deal with molar mass, stoichiometry, molarity. All of these things we will be using as we go through not only this lesson but some other lessons in Module 7. Since this is 7.03, we also need to make sure we've completed 7.01 and 7.02, dealing with acid-base properties and definitions, the neutralization reaction, and then some review on concentrations. If you are not feeling comfortable with any of these lessons, please go back and review them. You can also watch recordings, attend open tutoring, but make sure you are comfortable with this material before you move on to lesson 7.03. Alright, the first thing that we look at in this lesson is the relationship between pH and water. Well, first, before we look at that relationship directly, we need to backtrack just for a second and talk about water by itself here. Water is said to be amphoteric, and that simply means that it has the ability to act as either an acid or a base, depending on the properties of the other reactant that it is reacting with. Alright, so if it's reacting with an acid, it will act as a base, and then vice versa. If it's reacting with a base, it'll act as an acid. Now, water by itself, therefore, does react with itself. Alright, so on the bottom here you see that we have a reaction where we have one water molecule reacting with another water molecule. Okay, and this is basically a double replacement reaction. So what happens is one of the waters will give up one of its hydrogen ions, and the other water will accept that hydrogen ion. So after you remove an H, on this side you just have OH. Because the hydrogen ion carries a +1 charge, what's left behind is a -1 charge. And then the other water has included that H+, so now you have H3O+. So you have your two products here from that double replacement reaction. Now, going back to our definitions in lesson 7.2, the first water in this case, the way we drew it up, donated hydrogen to the second one. So the first water here was acting as the acid, the second water was acting as the base. We also learned in those earlier lessons that we can also do the reverse reaction. So in this case, for the reverse reaction, the hydronium ion, the H3O+, is donating to the hydroxide to get our original products, or our original reactants. So in this case, this is our acid, and this is our base going in the reverse reaction. Now remember, to distinguish that we're going in the reverse reaction, we put the word conjugate in front of those. Alright, so that would be the conjugate base. The hydronium is a conjugate acid. And again, that is when we're doing the reverse reaction. Okay, and we learned that back in lessons 7.1 and 7.2. Alright, so water, again, can act as an acid or a base. Alright, so some other key points here about this self-ionization of water, which is what this really is, right? Water reacting with water making ions. So that's why we call this self-ionization of water. First point is that we often refer to this as hydrogen ions, as far as the H3O plus over there. But we want to be sure that what we're really talking about is hydronium. Okay, so realize that when you hear the phrase hydrogen ions or hydronium ions, we're talking about the same thing. Because really, that's all this is, right? It's just a water molecule with a hydrogen ion attached to it. So when they get connected together, we now have hydronium. Second point is that because it is a self-ionization situation, when it's pure water, the hydroxide and hydronium ions are equal to each other. We have equal amounts of both, equal concentrations of both. Because happens in a very small amount, this ionization, it is going to be a weak acid or base. Remember back in, again, 7.2 and 7.1, we talk about the ionization. If it's 100% ionized, it's considered a strong acid or base. Anything less than that would be weak. Well, in this case, water does not completely self-ionize. All right, when we're drinking water, we're not drinking OH minus and H3O plus. We're drinking H2O with a few OH minus and H3O pluses in there. So it is a weak base or acid. As a result, it is a poor electrolyte. Remember, we do need ions to conduct electricity. Okay, and that was something we learned back in Module 3, 3.06. So since we have a very weak acid, there's not going to be very many ions. Therefore, it's not going to conduct electricity. The other reason for that is if you go back to our equation up here, we are making equal amounts of negative and positive ions. So of course they're going to cancel each other out, so overall you're really ending up with a neutral substance. We're not going to be able to conduct electricity. So with all that said then, pure water is considered neutral because again it contains equal amounts of both of those ions. All right, so what happens then if we add more of one or the other? Okay, so let's say we take HCl, hydrochloric acid, and we add that to our water. Again, the acid will donate hydrogen to the base. So again, we already know HCl is an acid. It's going to donate hydrogen to the H2O, so in this case the water is acting as a base. So now we have the Cl minus ion, the chloride ion, and we have the hydronium ion, the H3O plus ion. So in this situation we have added more hydronium ions. So when we compare the two concentrations, we have a greater amount of hydronium ions than we do hydroxide ions. This would be considered an acidic solution. Right? Same type of thing would be true if we added a base. Again, if we take some pure water and we add ammonia to it, NH3, which is a base. In this case, the water would act as the acid, right, showing its amphoteric abilities, and it donates a hydrogen to the ammonium. So now we have just OH with a minus charge, and we have NH4 plus. So we have added more OH minus ions, hydroxide ions. Since the hydroxide ion concentration is higher than the hydronium ion concentration, this would be considered a basic solution. So you can almost kind of think of it like a teeter-totter between those two ions. When it's perfectly balanced between the two, we have a neutral solution. If it goes one way or the other, so if the hydronium goes up and the hydroxide would go down, we're going to end up with an acidic solution. If it goes the other way, the hydroxide goes up and the hydronium goes down, then we end up with a basic solution. Okay, so here's just kind of a summary of everything we were just talking about. Acidic, more hydronium. Neutral, they're equal. Basic, more hydroxide. Okay? Now, a lot of times we are dealing with very small concentrations of both the hydronium and the hydroxide ions. So instead of using these really small numbers, we like to use what's called the pH scale. And the pH scale is simply a numerical scale that indicates hydronium ion concentration. The scale goes from 0 to 14, and we'll show you here in a second where those numbers come from. 7 is neutral. If the pH is less than 7, it's acidic. If the pH is greater than 7, it's basic. Now the formula that we use to figure out pH is this one right here in the middle of the screen. pH equals negative log of the hydronium ion concentrations. Remember in Module 5 when we talk about concentrations we put square brackets around it. So when we say the square brackets, we are talking about hydronium ion concentration. So we take the negative log of the hydronium ion concentration. Now to get the concentration, again back in Module 5, remember that is moles of solute per liters of solution. So you may have a problem where it says you have so many moles of the acid and you dissolve it in 500 milliliters, what would be the pH? So you'd have to first calculate the molarity, then plug it into this formula to get the pH. Okay, so just a quick example here. What is the pH of a 1.2 times 10 to the negative 5 molar nitric acid solution? Okay, so we know it's an acid, so we're just going to plug it into our formula here. Negative log of 1 times 2 to the negative, or times 10, excuse me, 1.2 times 10 to the negative fifth molar. Alright, so grab a calculator that does logarithms for you. And take the negative log of 1.2 times 10 to the negative 5. And you would end up with 4.92. Okay, so the pH, 4.92 is less than 7. So that tells us this is acidic. All right, so just doing a quick self-check, in the problem it says we have nitric acid, and we end up with a pH in the acid range, so that means that we're probably correct as far as our final answer. Now, one note here, on the scale, remember we said that anything less than 7 is acidic. Well, if we are closer to 7, since 7 is neutral, that would be considered a weaker acid. Okay, so on this end, as you get closer to 7, you would have a weaker acid. As you get closer to 0, you would have a stronger acid. So for this one, 4.9, we're kind of like right about in here. So this would be towards the weaker end of the scale as far as being a strong or weak acid. All right, now I mentioned a moment ago that the pH scale is from 0 to 14. Reason for that is because if you're given the hydronium, or excuse me, the hydroxide ion concentration, and you are given the hydronium ion concentration, we can actually calculate what's called the ionization constant of water. Okay, reason for that, if we go back to the neutral water, remember we said it had a pH of 7. Okay, well that pH comes from taking the negative log of the concentrations. Well, when we have that neutral water, the concentration of the hydronium is 1 times 10 to the negative 7. And the hydroxide, remember they are equal, it is also 1 times 10 to the negative 7. So when we take those two numbers and multiply them together, we get 1 times 10 to the negative 14. If we take the negative log, so if we take the pH of each of these, or use that pH formula I should say, we would end up with 7, 7, and 14. Okay, so that's by taking the negative log of each of these concentrations. We would get these numbers. So the scale is 0 to 14, and that 14 comes from this constant, and 7 is neutral because that's when the two are equal. So if we are given a pH value, then we can easily figure out what's called the pOH. All right, this one, because it was for the hydronium, that's the pH. This one, because it's for the hydroxide, is called the pOH. So if we used our example from the last screen, remember we had a pH of 4.92. So if we wanted the pOH, we could simply take 14 and subtract the 4.92. And that would give us a pOH of 9.08. Now that same type of reasoning works for concentrations. So again, using our last example there, we had, if I remember correctly, it was 1.2, sorry, it's supposed to be a 1, there we go, times 10 to the negative 5th, and we would multiply that by the hydroxide ion concentration, and you set that equal to 1 times 10 to the negative 14. So if we divide both sides by the 1.2 to the times 10 to the negative 5th, that would get us the hydroxide ion concentration. Because again, when you multiply those two together, you always get the 1 times 10 to the negative 14. And if we did that, we would end up with 8.3 times 10 to the negative 10 molar. Okay, so that's how we use that relationship. So we can find concentration of of hydronium, hydroxide. We can also find pH, we can find pOH. All right, so here's just some rearranging of that same formula. Again, just showing how we can get the concentrations of any of those. Another formula that we could write in here is pH plus POH equals 14. Okay, so we can use any combination of these to solve for any of those variables that we're asked for. All right, so let's try some here. All right, we want to know the pH of a 2.3 times 10 to the negative third molar NaOH solution. Okay, well, NaOH, remember this is a base, and we know it's a base because of the hydroxide ions, right? We have OH minus that should have a bell going off in our mind saying this is a base. So first thing I need to do then is figure out the hydronium ion concentration. Alright, so going back to our previous screen, we do that by taking the 1 times 10 to the negative 14 and dividing it by the hydroxide ions. So we're going to divide it by the 2.3 times 10 to the negative 3 to get our hydronium ions. Okay, and that gives us 4.3 times 10 to the negative 12 molar. Now we just simply plug into our pH formula. So the pH equals the negative log of 4.3 times 10 to the negative 12. And that would give us a pH of 11.4. Alright, so we end up with a value greater than 7, which tells us it's basic. And again, at the beginning, we said we had a base, so our number makes sense. Our answer makes sense. Always want to check to make sure those answers make sense. Alright, let's try another one. We want to know the pH of a solution with a concentration of 7.4 times 10 to the negative 4 molar hydronium ions. So this one, they already give you the hydronium ions, so we just simply have to plug it into our formula. So the pH equals negative log of 7.4 times 10 to the negative 4. And that'll give us a pH of 3.13. Now, if this problem asked for POH, which it didn't, but if it did, remember we said pH plus POH is equal to 14. So to get the POH, we could just take 14 and subtract the 3.13. And that would give us a POH of 10.87. Okay. All right, so another one. What is the pH of a solution with a concentration of 4.2 times 10 to the negative 3 molar hydroxide ions? So again, we have the hydroxide ion. So we have to first get the hydronium ions to plug into our formula. So to get the hydronium ion, we take the 1 times 10 to the negative 14 and divide it by the hydroxide ion concentration, which we just determined was 4.2 times 10 to the negative 3. And that's going to give us 2.4 times 10 to the negative 12 molar. And then again, our formula for pH is to take the negative log of that number. And that gives you 11.6 for a pH. And again, that makes sense because it's over 7. We have a basic solution, so we probably have our answer correct. All right, now the one final thing is sometimes we're given pH and we want to find out the concentration. Well, in math, you may have already learned this, that to work backwards with your logarithms, you have to take the base 10 and put it to that answer. Okay, so in other words, if you're looking here at our formula, the hydronium ion concentration is going to be the base 10 to the pH value. Now we have to include the negative sign because we have it here in our original formula. So this is a part, you may have not seen the negative issue there in math before, but for us we have to use it because of the negative sign here. So in this example, it says, well, what's the concentration of the hydronium ions if we have a pH of 2.3? All right, so again, just like we were doing before, we just plug it in. So 10 to the negative 2/3, or 2.3, excuse me. Plug that into your calculator and you end up with 0.0050. In scientific notation, if we move that decimal point over, this would be 5.0 times 10 to the negative 3. Okay, so simple as that. And just plugging it in just like we did with the pH formula. All right, now the one final thing is sometimes we're given pH and we want to find out the concentration. Well, in math, you may have already learned this, that to to work backwards with your logarithms, you have to take the base 10 and put it to that answer. Okay? So in other words, if you're looking here at our formula, the hydronium ion concentration is going to be the base 10 to the pH value. Now we have to include the negative sign because we have it here in our original formula. So this is a part, you may have not seen the negative issue there in math before, but for us we have to use it because of the negative sign here. So in this example, it says, well, what's the concentration of the hydronium ions if we have a pH of 2.3? Alright, so again, just like we were doing before, we just plug it in. So 10 to the negative 2/3, or 2.3, excuse me. Plug that into your calculator and you end up with 0.0050. In scientific notation, if we move that decimal point over, this would be 5.0 times 10 to the negative 3. Okay, so simple as that. And just plugging it in just like we did with the pH formula. Alright, so let's try one. What is the hydronium and hydroxide ion concentration of a solution with a pH of 11.4? Alright, so going back to our formula from the last screen, to get the hydronium ions, we take base 10 to the negative pH. So in this case, negative 11. Alright, we plug that in to our calculator. 3.98 times 10 to the negative 12 molar. Okay, so now going back to our concentration formula, remember to get the hydroxide ions, in this case, we would take the ionization constant for water, 1 times 10 to the negative 14, and divide it by the hydronium ions. So on the bottom it's going to be 3.98 times 10 to the negative 12. Alright, and that will give us 2.51 times 10 to the negative 3 molar. And again, this one is for the hydroxide, and the top one is for the hydronium. Alright, now 11.4, that tells us it's a basic solution, which means we should have more hydroxide ions than hydronium ions. So if we check our answers, 10 to the negative 3 is definitely a much bigger number than 10 to the negative 12, so our answer makes sense. You always want to check that when you're done. Alright, so now we have a better understanding of pH and concentration, how they relate, how we calculate it. We can now use that in a laboratory situation, and we call that a titration. So some terms here that we're going to use: titration, burette, stopcock, stoichiometrical equivalent, endpoint, acid-base indicator, and a titrant. So let's just go ahead and kind of walk through each of these a little bit and how they work together. First off, a titration is just simply a lab method in which we determine the concentration of an unknown acid or base by using a known acid or base. Okay, so let's say, just for an example, you have some hydrochloric acid and you have no idea what concentration it is. Well, if you have some sodium hydroxide with a known concentration, say it's like 0.1 molar, then we can actually go through this process of titration, get to the point where they neutralize each other, and then be able to do some calculations based on that. Because remember what we talked about earlier, when they neutralize each other, we have equal amounts of hydronium ions and hydroxide ions. So basically at that moment then, we know the concentration of the NaOH, therefore we can figure out the concentration of the HCl based on doing some simple calculations. So what does the experiment actually look like? Well, in the lab setting, the main instrument you're using is this long tube that kind of looks like a graduated cylinder. It's called a burette. It's a narrow piece of glass, and it has gratings on it just like a graduated cylinder does. At the bottom, it funnels into a really skinny drop area right here. And this basically will allow you to do it drop by drop. The stopcock is basically the little valve right here that you use to open and close the burette to release small amounts of what we call the titrant from the burette. All right, the titrant is the one that we know the concentration of. That's the one that goes in the burette. The one that we're trying to figure out the concentration of is the one that we put down here in the flask. And we're going to chemically mix with it. Okay? Now, as we are adding that known concentration of acid or base, we add it until we get to what's called the stoichiometrically equivalent amounts. In other words, we have equal amounts of both. This is called the end point. All right, the end point. Once the acid and base concentrations are equal, we have a neutral substance. pH is less than 7, or excuse me, pH is equal to 7. That is called the end point. Now there are a few different ways that we can figure out when we've reached the end point. One way we can do that is with a pH meter. All right, and that's pictured right here. This instrument, it looks just like any type of meter you may have come across, like a voltmeter, things like that. It uses this electrode. You put it in the solution, and there's a couple of electrodes in there that do some measuring for us. We won't get into all the details of that here, but it gives us a reading on the screen as to what the pH is. This is a very precise way of figuring out our pH values as we go. So obviously once that hits 7, we know that we've got what we need. Another thing we can do is we use a acid-base indicator. All right, an acid-base indicator is simply a chemical that changes colors depending on whether it's in an acid or a base. Some of them switch between yellow and blue, some go between red and yellow. There's all kinds of different combinations. The most common one that we use is phenolphthalein, which is clear in an acid and then turns to a pink magenta kind of color when it's in a base. So we can use just a drop of phenolphthalein, and when it changes colors between depending on if we started with an acid or a base, if it goes clear to pink or pink back to clear, whichever direction we're going, that tells us we've reached the end point and we stop adding the titrant. Okay, so it's a much, it's a qualitative method, definitely cheaper because we're only having to use a drop of it versus having to buy a pH meter. But of course the pH meter would be more precise because it is giving us an actual readout. So there's pros and cons to using both of these methods. Okay, so again, the most common indicator that we use is that phenolphthalein. Add a drop of that. If it's in an acid, it's clear, and if it's in a base, it will be pink. So let me just mention that up here. Clear in a base, or in an acidic solution. And that's one of the main reasons why we like this one, because it goes clear to color, whereas the other ones usually go between two different colors. So it's a little harder to determine when we have actually reached the endpoint. All right. So as you're doing the lab, I do want to mention that you have to be very careful to stop at the right point. You want just a very faint pink color in it. If you added another drop to this, it will tell you that you've gone too far, and it will actually turn to a bright magenta. Alright, so that concludes lesson 7.03. Make sure you complete all the example and practice problems. Watch any videos and hyperlinks that may be located in the lesson. If you still need some extra help, please attend one of the open tutoring sessions and we will definitely help you out with that. There's also a review sheet in the Student Resource Center you may use. For this activity, you will be completing the 7.03 virtual lab, and you will be doing a titration in this lab. If you do need assistance with that, we do offer a completion session, so you can check your teacher's announcement page for the upcoming 7.03 completion session.